Hello everyone, my name is Agramil Al-Fuad and I'm gonna be presenting on behalf of our team the research entitled A Traffic-Aware Street Lighting System based on Fuzzy Logic Controller. Street lights account for more than 19% of global electric consumption and up to 40% of a city's energy budget. Particular interest is given by the scientific community to street lights due not only to their energy consumption but also for their importance in the safety and well-being of road users, especially in some peculiar locations where a high chance of theft or crime may occur or where connecting lamps to the main grid is challenging. A solution is to install standalone PV-powered street lamps because of the unlimited green energy provided by the sun and the absence of additional wiring. However, these systems are affected by low amounts of solar radiation, especially at winter, and due to the unwise way of operating this system, such as providing 100% brightness at non-existing traffic, leads to a quick battery depletion and may jeopardize safety. A conventional control method found in the literature is through the use of wireless sensor networks, where the brightness of street lamps can be adaptively adjusted according to the sensed traffic volume or other meteorological parameters. For example, if the traffic volume is high, then the brightness of street lamps is adjusted at full brightness. Or at low traffic volumes, the lamps are dimmed to a certain level. Previous works applied this control method on grid-connected street lamps. However, since these systems are powered by batteries at night, the battery level should also be considered in the control. So, the goal is to find a compromise between the forecasted traffic flow and the stored battery energy, which can be achieved through the usage of a fuzzy logic controller. In our proposed control method, we first start by forecasting the hourly traffic volume by using previous values. Then, once the traffic volume in the current hour is known, the fuzzy logic controller takes the future traffic need and the battery energy to make proper dimming command. In order to evaluate a traffic forecast model, we make use of an open repository, which is the Caltrans Performance Measurement System. We choose a one-way route containing 4 lanes, which is the E56 in California, District 3, Sacramento. Nevertheless, in this study, we limit the traffic prediction to the aggregated traffic flow values of all lanes in one direction. The data is sampled into 1-hour samples from 1st January to 30 June 2021, making 4,320 observations. The data is then split to 80% for training, validation, and 20% for testing. The evaluation of the prediction accuracy is achieved through the use of root mean square error and the mean absolute percentage error. The first considered model is a parametric model known as SARIMA. This model incorporates both seasonal and non-seasonal components in a multiplicative manner. In order to identify each parameter, we first start by inspecting the data visually and by plotting its corresponding histogram. We can observe from the figures a non-normal distribution and a visible seasonality in the original data. And by performing a statistical test, the obtained p-value of the ADF, PP, and KPSS tests are 0.01. Both the ADF and PP tests suggest that the data is stationary. Nevertheless, the KPS test should give a value higher than 0.05. Thus, assuming the stationarity of the time series is unsafe. Since the data is hourly, we difference the data by one seasonal lag, which is 24 hours. And again, by inspecting the differenced data, we observe that the data has become normally distributed. And by performing the KPSS test, a value of 0.1 is obtained, which indicates that the data is now stationary after using one seasonal differencing, which is d equal to 1. To identify the other parameters of the SARIMA model, we use the AutoArima function in Python. It tests different combinations of PDQ and PQ parameters to find an optimal model. We specify the seasonal differencing as d equal to 1 and set m equal to 24. The best model is identified as a SARIMAX with the parameters are 100,212, and the obtained score results are 300 97 vehicles per hour and 15.2% for both the RMSE and the map test. We also use two non-parametric models, which are an artificial neural network containing one hidden layer with 100 units and a deep neural network with two layers containing each 164 units, respectively. In this case, the size of the input layer of each neural network is specified by the window size, which means the number of previous observations. We use grid search to find the optimal hyperparameters for each window size, and then we measure in each case the forecasting scores. In both cases, we observe that a time window of 24 hours yields the best scores. Here we see a comparison between the best traffic forecast models. On weekdays, all the traffic forecast models perform well. However, during holidays, we can see that both the artificial neural network and the deep neural network models performs better than the SARIMA. From this analysis and the obtained scores, it is evident that the deep neural network with 24-hour time window outperforms all traffic forecast models. Thus, we use this model for traffic forecast in the proposed system. For the fuzzy logic part, both traffic and the remaining battery energy were normalized from 0 to 100%, while the light level ranges from 0 to 1. We used low, medium, and high as linguistic variables to describe both inputs and outputs. The inference rules are a combination of all possible inputs. For example, if traffic is medium and battery energy is high, then luminosity is medium. To simulate the system in MATLAB, we consider that street lamps are equipped with 30-watt LED modules. The lamps are considered active for 10 hours a day on average, with a required autonomy of 3 days. Thus, based on state-of-the-art calculation, a 100 ampere-hour battery size is used to power the LED lamps. For the model evaluation, we compare it against the traditional light control with no dimming and a control method based on traffic. In the first case, we start at a battery level at 100% and simulate for 11 hours of nighttime. Simulation results indicate that the remaining energy in the battery is 85%, which is higher than the other control methods. However, in some cases, the power generated during daytime may not be sufficient enough to charge the batteries. For example, in winter, nighttime is longer and daytime is shorter. The second figure showcases this scenario, while assuming the initial battery energy is 50%. For a 15-hour nighttime duration, the remaining energy in the case of the fuzzy logic system is 37.25%, while 25 and 12.5% remains in the case of traffic adaptive and no dimming, respectively. As a conclusion, in this paper we proposed a light controller for PEV-powered street lamps, which is able to adjust lamp brightness according with the remaining battery energy and traffic volume, thus decreasing the consumed energy and ensuring safety for road users. In future work, we will consider the future energy production of street lamps and other forecast models, while taking into account the cooperative light from advertising panels or stores. Thank you for watching this presentation.